He's the example of what some of the pathways can be if you were to go through his 10-month NIH program. He chose to become a researcher, do more in this area, and one of his reasons was that he had a better understanding of energy after going through school. So obviously this is a pathway other than people just going into the corporate world or the energy field. This is a very interesting pathway. But more than that, Kwame has been a very strong friend of ESCI. He's been mentoring many of the incoming students, and they found it very valuable to hear from somebody who's gone through it. He's doing his PhD in the electrical and computer engineering department, and it's in fact related to what he's going to be talking about. Grid resilience is a very hot field. Again, how many of you know what resilience is? Yeah, good. Which is resilience. What does it mean to you?
Oh, I have to answer? I was bluffing, actually.
Oh, okay.
No, I'm kidding. I think it means the capacity to endure some sort of shock or failure to the system and respond.
Wonderful. That's terrific. Okay.
I made that up.
Yeah, you made it up, and you got experience, so you're obviously resilient. You know the word. Resilience, actually, more accurately. Sorry, I'm not getting what you're saying, but it's not just you cannot prevent a grid from going down during an extreme weather event. It is how quickly does it come back? Your customers want to know. All right, I accept the fact that the grid is down, but I want to know when's it going to come back. And it's something that's reassuring, even if you say 12 hours, you give them a good reason, then they understand. Severe weather has a problem with our grid. It always affects our grid. But if you can reassure, say, it's going to be back in a certain amount of time, people. And so this is a very hot field. In fact, there are FERC orders which require resilience to meet certain standards. Hurricane Sandy was a classical example where things went, kind of failed pretty badly. We're learning a lot of new lessons there. Kwame's going to talk about what are the pathways to sustainable and resilient grid. As I said, his PhD is along those lines. His advisor is Dr. Shalini Kishore. That's her. He's interned at PJM. In fact, one of his advisors is part of our advisory team here. And at PJM, as you know, PJM is one of the biggest grid server in the world, in fact. He got his master's at the University of Lome at Togo, and we're very glad to have Kwame present the material. Thank you, Kwame.
Thank you. The subject we're going to discuss this afternoon is about sustainability, resiliency, and reliability. These are, I may say this is a broad topic because there's a lot of things that are involved when we talk about sustainability, resiliency, and reliability. But we have about 40 minutes to talk about it, so I won't go in much detail. If someone is interested in more thorough discussion about these and the work that we're doing in this field with regard to our PhD, I'll be happy to discuss. And as a matter of fact, we won't see equations here because it's a lot of math involved, but we won't show any of those equations. If someone is interested in seeing those groups, we can talk about it later. So this is the overview of our discussion. We'll first go through the motivation, why it's important to talk about this, and then take each piece one at a time. And it's a hard exercise because they are interrelated, but we'll try to go through them as we go through them. So what do we mean by sustainable? Because this can have so many definitions. So we want to make sure that we're on the same page as we talk about sustainable growth here. Something is sustainable if it meets needs of the present without putting in jeopardy the future generations. So if we're talking about with the sustainable grid, we want to make sure that we have a grid, which is a system of things that is working right now, meeting our needs, but doesn't create other problems for future generations. So along those lines, sustainability is always related to environment, which is what we're going to talk about. We can have sustainable economics, for example. So if you're selling something or doing business, you want to make sure that the business doesn't interfere with the future of other generations, for example. But here, especially, we'll focus on environment. So as you can see here, okay. So we have the chart of the different components of the electric grid, from the generation to the consumption, homes, going through all the other components that are on the line, transmission and distribution, for example, with all the equipment, automation, control that is involved. So if we talk about sustainability, we want to make sure that it's related to every single phase of this chain. For example, generation has to be sustainable. That's where the biggest problem is. Because we will see, as we will see later, the chart showing how much impact it has on the environment in general. A resilient grid, simply put, we'll say it's the grid that actually keeps the lights on no matter what. So even in extreme conditions like hurricanes, earthquakes, flood, or other cases where the grid is actually affected. But we want to make sure that we have a minimum of comfort level that is satisfied on the consumer. So the resiliency events that can be classified as part of resiliency events are generally low probability and high impact events. A reliable grid, reliability is everyday thing. So on the other side of resiliency, which is maybe once a while thing, reliability is everyday, every single day thing, where the energy that is produced in the power plant has to come down to the consumer. And anytime we flip the switch, we want to see the light. So how does that happen? The grid has to be reliable to be able to give us any time we want. So that's what we'll be talking about. And in the everyday operation, there might be problems like faults. There might be other things that need to be addressed real time so that we can have energy. So those fall under reliability. And these are high probability events that we know are going to happen. And they happen often. So we are prepared, we're better prepared. But they don't have that much impact because we have the tools to counteract them. Okay, just gonna. Okay. So now that we've seen why we need to care about these three topics, we're going to talk about sustainability. one of the reasons why we care about sustainable grids is the fact that electricity is a major component in greenhouse gas emission. This chart shows the situation in the US in 2014, where electricity account for 30% of the emissions. Talking about greenhouse gas emissions, we want to mention mostly CO2 emissions, because that's the biggest part of the emissions. So if electricity has that much share in the emission, what do we need to do about it? We can also see that the generation, this is in 2015, in the generation across the US, 2/3 of the generation come from sources that can pollute or can emit CO2, like natural gas and coal. These are 2015 numbers, 33% each. But now I think the trend is toward natural gas with 39% or 40% or so, close to that now, while it's decreasing in the coal plants. But still, we know that natural gas is not 100% clean. So we need to care about this. Because on the other hand, we only have 1/3 that's coming from low emission sources or low to free emission sources like renewables, hydro, nuclear. There are debates about hydro being renewable or not, so that's why we distinguish them here. Hydro with 6% and renewables, other renewables, 7%. So what should we do about this? Knowing that these sources are 30% responsible for the emissions, and we only have 1/3 of our fleet, which is non-emission sources. So the easy things to think about right now is just to increase the share of those non-emission sources like renewables, which is basically what all the RPAs are about. So, as I said, we need to increase the share of the renewables in our fleet. And these can be done also by lowering the impact of conventional sources. For example, people talk about clean coal, like other technologies to limit the emission from the conventional sources. So these need technology refinement and, for example, carbon capture and sequestration, which is a big debate. We're not going to enter into the debate whether or not it's a feasible or enjoyable solution or something that we would like or not. But these are what we can quickly see as a solution to the fact that we have a large share as an energy industry, we have a large share into the emissions. So this said, well, we're going to talk about a little bit about renewable integration and some of the challenges that are involved. So if we say to be able to reduce the emissions from electricity generation, we want to include or increase the share of renewables, there might be problems that are related to renewables as well that can actually affect all the qualities that we have now, the qualities of the electricity we're using, especially reliability. So because the generation from renewables is pretty uncertain, which means that, okay, if I put a solar panel. What if the sun doesn't come out? What will happen if I rely only on solar panels? What if it's a cloudy day? What's going to happen? So I will flip the switch and nothing, because nothing is there. If I rely on wind, for example, 100%, if I assume I have 100% wind and the wind doesn't blow, so what? Which means that grid reliability will be affected some way if I only count on renewables without any mitigation strategy or technology behind my decision. That's why even now we still rely on other sources, the conventional sources, because they're there. If I need energy, I'll just turn them on, and the market will make sure that energy is available to everyone, unless there is extreme cases like hurricanes and other things that there's nothing to do about it. And these also, renewable integration will affect planning and operational tools. If we don't have good planning tools or operation tools, we may have renewables, but we're not going to be able to use them. Let's take an example. At midnight, there is no sun. So if there is nothing, for example, to store, if I rely completely on solar and there is nothing to store energy during the day, at night, I won't be able to take a warm shower, right? It's going to be all cold, and that's what I have. So we also need to think about transmission assets. We have a wind farm that is remote, somewhere, because that's where the wind is, and we build a plant there. We need to carry that energy we're producing in that wind farm up to the consumer. So if right now in that region there is no transmission line, then we have to think about that as well.
Tommy, I have a perfect article. I think the time to ask the question is now.
Okay.
It's in the Wall Street Journal. It's very interesting. In Germany, during the sunny, windy days, they're making huge amounts of renewable power in northern Germany. And they need to get it to the industrial base in south Germany. They don't have the transmission lines. So it's flowing through Poland and Austria. So they have to turn off their power plants, which is the whole article that is. The grid is at risk by too much sustainable going on. And there's even arguments, and they're building phase shifters to block the power flow from Germany into Poland and Austria, keep it up in the north. So it's just, maybe it's more of a comment about exactly what we're talking about.
Yeah, exactly. So we may have power, but if we don't have the means to transmit that power from the generation side to the consumer, it's going to be of any good for us. There's nothing to do about it. And the fact that renewables are fluctuate, they're changing rapidly from high to low, for example, you will see that you have a transmission asset that can't take it at any time. It's not like every time, 24 hours, you're able to output renewables onto your transmission system, because you might reach the cap, because you just jump too high and you can't do anything about it. So these are the things we need to think about when we're talking about integrating renewables into the grid, because these are serious threats, actually, to the grid, if we think about it. Also, are they cost effective? Maybe, maybe not. Depends on the technology. Solar prices are coming down, but we know that in general, the investment cost, the capital cost is pretty high. So we have to take that into consideration when we're planning to replace the current fleet with renewables. And if one day we're able to have 100% clean energy, 100% renewables, we need to take into account all these changes. Is the technology ready? Maybe to some extent, maybe not. In other cases, the ratio, what the energy that is available versus the energy that we can actually output is not that interesting in a sense. That, for example, for solar, we don't have even 20% yet. There might be some demonstration going that are aiming for higher yields, but at this point, it's difficult to say. So all this is capped by social acceptance. For example, we heard about this NIMBY thing, not in my backyard. Everyone wants power, but no one wants power plants in their vicinity or close to their house. So it's a challenge. Unless people are willing to have solar panels on their rooftop, and that might be okay. But for other types of renewables like wind, how many people would like to have wind farm in their backyard or in their vicinity? That's other problems from social perspective. So these are the challenges that renewable or clean energy has to face to make it through the current stage to a real large-scale application, great scale applications that are significant enough to hold the grid. But I think we all are hopeful that one day we'll be able to answer these questions more effectively. So we saw that to have a sustainable grid, we have to have the clean energy, cleaner energy, because we're producing 30% of emissions, so we have to reduce that. But there are challenges. Okay, so we see that these renewable integration can be a threat for reliability, as the example in Germany just showed. We have power, but there's nothing we can do about it. We can't use it, basically. So we're going to talk about grid reliability next. So to be able to see the bigger picture of grid reliability, we have here a graph or a chart that shows the entire system from generation to consumers, where the gen codes are generation companies, ISO independent system operator, transmission companies, transmission owners, distribution companies, and the consumers. So let's say I have a friend. My friend will be reliable if anytime I need him, he's there. So it's the same thing for the grid. I'm paying for electricity and I want to be able to use electricity anytime I want to. If not, then there is a problem. These are all the entities that are involved in bringing the energy from generation to the consumer side. And I would like to highlight the word market, because it's a real market. No generation company is going to produce electricity for free. If you can't meet their needs, if they can't pay their employees, if they can't pay back their investment, they're not going to produce. So there is a market in which everyone submits his offers and we get cleared, and finally we have electricity. So talking about reliability, the problem is in the market, a day ahead or in a real-time market, we might still need some more energy to match the demand because no one asks permission, the grid owner, before flipping the switch. So instantly, I might need to do something as a system operator or as a plant operator. I might need to do something to be able to meet that demand. It's hard to predict the demand. For those of us who have been able to see a system operator control room, see how they do their studies, a month out study, a week out study, 3 days out study, 2 days out study, 1 day out study. It's a pretty tedious job. So all those studies, they are trying to figure out what the demand of the next day is going to be, what the demand of the next 2 days are going to be, what the demand of the month is going to be. So it's hard. When we flip the switch, it's a lot of things that are involved. And it's hard to predict who is going to flip his switch at any time and how much energy is going to ask from the grid. So it's pretty important that we keep this in mind, that reliability is provided by the market, through the market, because if the price doesn't make sense to Genco, he's not going to output anything. He will not go into that market. So, so now, talking about reliability, to be able to increase reliability or to maintain reliability in a high renewable penetration market or grid, we need these to be more flexible. The consumer side needs to be a little flexible compared to what we usually do, just flip switch those things. We need appliances, we need smart devices to be able to control our appliances, our usage. If there is a signal from the distribution system operator that, oh, we might not be able, we only have this much, or this is how much we would like you to consume, we need devices that are able to control our appliances so that we are in a way responsive to the distribution system operator. That's one of the things that is broadly talked about as demand response. So the ability for the end user to react to what's going on at the grid level is really important if we are to keep a reliable grid, especially with high renewables. And these also, so we talked a little bit about the devices. These also involve a lot of control and automation on the other side of the bridge. Can be generation, system operator, both bulk level transmission and distribution level. So we need things that are up to date that can handle these variations. Okay, so for demand response, there are so many programs that even if we want to talk about it all day today, we'll be here talking about them. But we will pinpoint some in some areas in which we work so that we can continue the discussion on them. So as I said, demand response is meant so that end users have the ability to participate, to play into the reliability of the energy they're using, the reliability of the grid. They can reduce, either choose to reduce or shift their usage so that supply and demand match all. So coming back to what you just said about Germany, this chart shows the load duration. So there is a problem here. The problem is that you see these values? I have 60,000 megawatt. I have about 25,000 megawatt. It's the same grid. But these are the levels of power that I'm actually asking the grid to provide at length. So I'm taking here 9,000 hours and rank them and see that it's only even less than 1,000 hours over 9,000 hours that I'm asking something that it's higher than 40,000 megawatt. The rest of the time, I'm asking something lower. But the transmission system needs to be built to be able to handle these cases. So this poses the question of efficiency. How efficient are we using the asset that we have? If only for few hours, I'm asking this much, and the rest of the time, I'm asking something less than 40,000, but I built my grid to stand 65,000. So there might be a waste somewhere. There might be a problem somewhere. So it'll be fun if we have just a flat line, right? So I built my transmission line for 60,000, and I just have like 55,000 all the time throughout the year. I'll be so glad, because then I know my investment, I'm using it efficient. But here's the problem. That's how our usage profile looks like, and it's pretty sad. It's difficult because of the investment that we make to build a system that can withstand this much, but we're only asking this for so many hours a year. So if we are able, as end users, if we're able to react to signals from distribution system operator, we'll be able to leverage some of the capacity unused here, or at least have a flatter, if not flat, because that's perfect, that's ideal, we can't achieve it, but have something that is more efficient in terms of energy use. So end users are given incentives, can be in the form of pricing or rebates or other things. But we're just going, because we're interested in the market design side of the thing, we're just going to talk about some pricing schemes that can help end users to respond to those signals. So if today I'm paying 10 cents a kilowatt, and no matter how much I use, no matter what time of the day I use energy, I'm only paying 10 cents. What's my incentive to change my behavior? Like, I will just keep doing the same thing, right? Like, there's nothing that's forcing me to change my behavior. I will shower when I want, I will do anything when I want, and I don't care. But actually, I have to care because of the grid reliability. If I care about reliability, I have to care about when I'm using energy and how I'm using it. So these pricing schemes, here I have real-time pricing, which is I just gave an example of price signals throughout the day. So it can change, that's the red line, it can change per hour, and it's given day ahead so that consumers know at this time, this is how much the electricity is going to cost you per kilowatt hour, and so on and so forth. We have another pricing scheme, which is time of use. That's the black dotted line. So that gives me, for, let's say, a season from January to May, for example, this is what you're going to be paying if you use electricity. So these prices are in $1 per kilowatt hour. And if you use electricity from 1 a.m. to 5 a.m., this is how much you pay, 0.09, basically 9 cents per kilowatt hour. And from other time you have different prices. So that's one thing that is done so that people can respond to prices. So by the way, the real-time price is calculated. It's based on the forecast of the generation and how much it's going to cost system operators to bring that energy to end users. So that's why it's changing. It reflects the wholesale price signal. But time of use is pretty stable. So here, the end user is somehow shielded from the wholesale fluctuation, hourly fluctuation, but still has to incur some of the costs. We designed this. That was last year in a research paper. We designed a new pricing scheme, which we call Gen Minimax pricing. And this graph right here shows how it works. So what we came up with is that for every single, so in the time of use, for example, in the time of use scheme, everyone is paying the same thing, no matter how much you are using, even if you are not against the signal, you are still paying the same thing at the given time, just as your neighbor. But in Gen Minimax, what we have is it differentiates users. So everyone has his own level B according to his history of use, energy usage. So for that particular day, based on the optimal the optimal signal, supply signal of the distribution system operator, he will set a B, a level B, a threshold B, and there is a gap under that B, so that if you consume anything less than B minus delta, you will pay C low. It's a rate. But if you consume anything in the band B minus delta to B, you'll pay a pretty low price per kilowatt hour. And if you go above the threshold B, the optimal threshold B, then you'll pay C high. So these are the levels of those. And as you can see, it's a threshold band 3-rate pricing scheme. And we did some simulations on this to show that Gen Minimax pricing actually outperforms time of use and real-time pricing because it differentiates between customers. We can be neighbors. You'll pay something for electricity that hour, but I won't pay it just because I'm not against the signal. So, of course, this poses the question of how well can you implement this? Do we have devices? Do we have the technology to track per user, to track every single consumer's usage and be able to determine in real time these thresholds and delta and everything? Well, it is feasible if we are able to communicate between the ESOs and the consumers. If you have smart devices, energy management systems that can actually track this and schedule, that's the most important thing, and schedule the load. Because if I'm not home, or if I'm home and I want to do something and I have to do it myself, then what's the point? Like, I'm not going to continue checking all the time, every single second, and see, oh, how much should I consume this time? So we need to have smart devices where we can have, so we have our appliances, our loads connected to the device that can actually schedule, based on the signal, schedule our usage. So we'll be able to achieve something like this. But if not, well, it's a pretty good research topic, right? That will end there. But to be realistic, we need technology to reach that level so that we can implement it. So pricing is key. Again, if I'm paying the same thing, I don't worry about anything. I just use what I want. But if I have to pay for reliability, if I'm kept accountable in grid reliability, then I might change my behavior. Social science majors will tell me that's true.
Don't count on it.
Okay, now we reach the resiliency part of the presentation. So before we go into it, I just want to say that reliability has to be a prerequisite for resilience. Because reliability is everyday thing, but resilience is once in a while thing. So the system has to be reliable first so that we can talk about resilience. So all the technology, assets, everything that is needed in reliability is still needed in resilience. So here I have the chart showing the outage frequency across the years from 2000 to 2014, where we see significant increase. This includes other types of outages, but about 60% of those are weather-related events or resiliency type of events. And resilience is trapped between or among extreme weather, ice storm, hurricanes, tsunamis, and earthquakes, flood, and things of that sort. And also cyber physical attacks. Because all we've been saying so far is that we need technology to support demand response, for example. And we need the grid to talk to consumers. We need consumers to talk back to the grid. And all this is going through communication channels. And this can be hacked. So we're trying to solve a problem. But eventually, we're going to create other problems. Because now everyone can talk to the grid from a smartphone. What if it's hacked? So we also have to be concerned about cyber physical attacks. So we actually need a more resilient grid against these type of events. And resiliency can be decomposed in three necessary parts. As I think 2 weeks ago or a week before this presentation, it was about the 2003 blackout. And we saw how the fault cascades and what needed to be done, what was not done. We saw all of that. And the three steps, the three necessary components of a resiliency program are prevention, recovery, and solvability. So we need to prevent, but we know that it's not everything that we can prevent. And so if it happens anyways, we have to have a plan to recover from it. And even if it happens, there is a level of comfort that we would like to maintain for our customers. So these are the three steps. It's we plan ahead. We plan ahead to define the strategies to use from design standards. What happened in Fukushima was basically the design basis was was not able to withstand what happened. So the plant wasn't designed to withstand that kind of event. So we have to act on the standards as well: construction, maintenance, inspection, and security, most of it. So on the recovery part of the story, we need to have outage management plans. We need to have assets that we can use if we need to replace, for example, a transformer. It's a major thing. But if we need to do it, we have to have this available. We have to have a plan ahead of the event. And on the third step, we want to survive even if it happens. So urgent services, do we have plug-in electric vehicles? We can power our house with electric vehicles if we have them, if we have them ready. And urgent services, things like lighting has to be on, even if something happens. We would like to take a shower and things like that. So basically, the takeaway from this slide is we have to plan ahead. We would like to prevent. If we can prevent it, we want to be able to recover from it, and we want to make sure that we have a minimum level of comfort that we maintain. Okay. So we give here an example of a recovery tool that we designed, and the aim was to be able to split the grid into microgrids when a disaster happens, so that we may recover quickly, because it's easier to manage a smaller system than to manage a big chaotic system after the disaster. So it's a model, it's an optimization model that we came up with that takes into account self-adequacy constraints. We also assume that we would have some truck-mounted distributed generations that can be moved around and placed at a specific location, so that we may recover more load as we can at this point. So taking into account demand responsive loads as well, and the network topology, whether it's at the distribution level, which is the radial network, or at the transmission level, a more mesh network. So it's an example of a grid 37 bus system with so the lines with these bars shows that the line went down after the disaster. These lines are closed permanently because of switching defaults, switching problems after the disaster. And so there are loads at these nodes, and to be able to recover as much load as we can, we have to run that model, that tool, that grid recovery tool that we designed. And this is what we came up with. So this is just an example to showcase how this works and how the solution, what the solution looks like. So we came up with three microgrids. We call them microgrids. They're actually subsystems. So 3 microgrids. Generation is here, generation is here, and generation is here. And these are the switches that we have to open to be able to operate these 3 islands separately, with the triangle representing the nodes. And some of the nodes are dispatched. Yes.
That generation was pre-existing on those microgrid subsections prior to the anomaly?
So we assume, good question. So we assume some generation might be there before the anomaly. So it's the case of this generation at 710. We assume that was there. And we assume that there are some mobile or truck mounted emergency generators that we can move around as well. So our model takes into account if you have mobile or fixed generations, so to come up with the best way to form the microgrid, to take into account flow constraints.
So some of the strategies include dispatching peaking turbines at substations, picking up geographic area that's served by that substation. Dispatching intermediates, because you can fire those up in like 5 or 10 minutes, pick up multiple substations so you can service that area, and coming back up in smaller segments. So ultimately you have enough that want to begin interconnecting the grid. But those are facilities that already exist.
Yes.
And technologies and practices that exist.
Yeah, so that would be the case. That would be the case of this generation, for example. But how do you come up with how far do I go? So the model gives you basically the set of nodes, the set of loads that you can pick up within. So, for example, that substation, which areas should you take for that substation to be fed by that substation?
Well, you know the history of the substation, and you know what it's doing because it's feeding that information back to the your dispatch center. So that information is real time.
Yes. So what if? So now you have a disaster. You have that substation. You have only that substation that is working. So you may not have the available capacity to feed the entire area. So you have to cut some areas. Like you have to open some lines. So this is what the model does for you. Identify which lines to open. So basically giving you the set of area, the subset that you have to pick up. Otherwise, because that was not the only one substation that you had in the system, the other ones failed. You only have that one remaining. If you have to feed the entire area with that substation, you won't be able to do it. So you have to open some lines and pick up just as much as you can so that they still have energy.
But that's really not the architecture from substation from sub-transmission transmission, which usually downward. So if you've got a peaking turbine at a substation, it's feeding its loads from that substation and why it stay from that substation, not going back up the system. Because typically that peaking turbine is not large enough to do that.
Yeah, but this is I think this is a distribution. This is a distribution level. Yeah.
In terms of the distributed generation, how much mobile generation could you expect to have? Do you have like megawatt level or
No,
smaller than that?
lower than that.
Or, so how do you decide how to fragment the grid based on your capacity, and then how do you supply fuel, whatever's needed over a period of time? Make sure you don't just connect it up to you run it 24 hours or whatever, then it's done.
So the fuel management is it's another scope. It's not the scope of this. So the assumption here is that you have the fuel available, so that you can start picking loads.
Well, if you're talking about trucks,
Yes.
you figure the horsepower, you figure the efficiency, figure how long it's going to run, unless you're talking about an oil truck. It's a whole, fuel for days.
Yeah. So the truck is not going to go from one point to the other and then go to the other. So here we find a location.
I understand that.
Yes.
But how much load are you picking up?
So how much load I'm picking up is based on the model. It's coming up as a, yes.
Kilowatts or?
These are in kilowatts.
Kilowatts?
Yes, all these are
They're
kilowatts.
really megawatts, right? You're talking about substation level.
Yes, so in a substation level, there will be megawatts, but these are in kilowatts. It's a IEEE 37 bus system, and all the loads are in kilowatts. So basically, if I have a 100 kilowatt generator, because we're talking about truck mounted generations here, it's not like a plant. So it's not much that you can do about it, but you can still pick some loads. We want loads like, for example, hospital or something that. So here we assign criticality factors to the loads. There are some that are critical, more critical than others. So all that is fed into the optimization problem that gives me which load I need to pick and how much of it I need to pick, because I can assume them to be demand responsive. So I can shed part of it. I assume I can shed part of it. I don't have to take all of them. So if I have 10 houses, if everyone can have lighting, for example, that would be good enough. Because this is an emergency system. It's not like you have to have 100% comfort level. So the load that I'm picking up is based on contractual parameter that I defined earlier that says, oh, hey, you are the distribution system operator, but if ever you need to shed my load for emergency, at least pick this much. So I can take a 100K generator and still fire houses, not only one, but because they're not using the entire thing that they have there, they're not at 100% comfort level. So from this, I get, again, the location of those and how much I'm picking. So takeaways, we would say that sustainability is really important. We need it. So we want to put renewable sources into the grid. But this adds another level of challenge to the grid in terms of reliability. So we can improve this using demand response and smart devices to be able to control, to respond back to the grid if need be. And as part of the problems that we can have cyber security problems. So we want to make sure that we think about that when designing any renewable, 100% renewable systems. And we need to have preventive actions and corrective actions planned ahead of any kind of disaster to maintain grid reliability. That will be all. Thank you.
We have a little bit of time just behind the classroom for questions. Yeah?
Well, I mean, maybe this isn't part of the study, but I'll ask you anyway. You can just say no if you haven't looked at it. As your percentage of renewables increases on the grid, the percent of large rotating machinery is probably going to drop. At some point, you get to a level where you have a problem with transient stability. And have you looked at that at all? Do you know what that critical level is in a percentage of total generation?
I don't know exactly that threshold, but you're right. As you increase renewables because of all these fluctuations, you need something to sustain basically to sustain the grid. Otherwise, it'll fall. So here, some studies say that we might need more reserve than what we have now to clip those variations. But the other thing is, if I use a natural gas plant to level or to compensate for those fluctuations, that means I will have faster ramping, which some studies say can aggravate the emissions. So there is a true problem, and this can be seen as technology problem. We have to solve those problems to be able to say, oh yeah, I want to go 80% renewables. 80% renewables, that's not going to happen tomorrow. The current stage of things that we have, I don't see that.
If I could another question on following along on that, but you mentioned the not a secret, there's a lot of coal plants sitting idle because gas plants have ramped up a lot over the last 10 years. So has there been a drop in emissions from electricity because they're burning natural gas and burning coal at how much?
Yes. So I think 2 years ago it was 32%. But from that study, 2 years before that study was 32%. So from that study it's 30%, which means they're going down.
Just to give a background to the question made by Alan, about 4 years ago, FERC issued a new rule that concerns itself with penetration of renewables on the grid, increasing impact on rotating reserves. It provides two things: provides capacity, energy, capacity and energy inertia. One of the problems with inertia is that it has an impact on the stability of grid voltage and frequency. So they have issued a new ruling that requires the interconnection to be responsive to an ISO's demand to increase its production of bars instead of watts. So you can get a ride through, but the problem with that is the payback on renewable is based on watts, bars. So if you give up watts, you give up the payback.
Yes.
That's a problem. They required, I think you're looking at somewhere in the area of 13 or 15% of renewables on the grid, and you have a rotating reserve of about 12 or 13%. So you get into marginal stability of the grid, and renewables do have a negative impact. What the latest thinking on that with respect to renewables is that when you put a renewable in, you will be required to provide 1 hour of energy ride-through along with that renewable so that you can cover those periods of time when the wind dies down or a cloud goes over your solar panel. And when you look at Hawaii Electric on the island of Oahu, what they did 6 or 7 years ago with installation of live wind turbines, is they required battery trailers at the base of the wind towers that could provide that energy ride-through as the wind barrier on the turbine, providing horsepower or kilowatts output.
Great. Good observation. Very good.
The greenhouse gas number that you gave for the penetration of gas, displacing coal, did that include the use of methane, or is it only just the combustion of greenhouse gas?
It's
There's a whole question about whether methane's escaping all over the gas network, right?
yeah, it's mainly sewage, which is basically 4%.
Regarding the NIMBY thing, NPR had a thing on this morning that said a guy just put in a windmill on his farm in North Carolina. It's very tall. Hired and they paid him $54,000 a year, so he didn't have too much.
Yeah, that's good. Good for him.
We have these balloon hoisted wind turbines, and they're really interesting research being done in that area. You'd really be out of sight.
Oh, float him up and put it in. Oh my God.
And the wind is very steady at certain altitudes.
Oh, I bet.
Any other questions? I've got some students asking questions. There you go.
Yes, I'm just taking a little blank reading so that I have a lot of questions. But the question I need to what do you think? Would you think what the would equate that? How do that makes the business generating into?
Well, thank you for this. So, rooftop solar will never compete with natural gas or methane, because again, investment cost is high, and so talking about stability of the system, the reliability of the system, if you're outputting, I think even in Pennsylvania, there are people that solar on the rooftop, they're producing the getting back the grid. And so far, they're managing it, so it shouldn't be a problem from a technology perspective, because how much is it? It's not even 1% of consumption, so that shouldn't affect the grid at this point. Those who have renewable
Sounds
energy.
like a great increase. 600 was for
Yeah, if 50% of houses in Pennsylvania, for example, they want to go solar, then I think TPL or whatever who they're dealing with has to solve the problem. If there is any potential of affecting the grid, by then upward, but most.
That's not PPL's problem. That's the owner's problem. That's what the standard requires. Before you get anything, you have to be sure you are in compliance with the government requirements. So it's the onus is on the owner of the renewable source going in.
Yeah, but the PPL issues the compliance, right? But for example, I'm connected to PPL.
No, compliance is a function of 1547.1, which is the conformity standard.
Yeah, but
The third element of that,
who pays them back?
The owner.
Like who pays them if I sell it to? Well, there should be an
actually, you're not really selling them. What you're doing is reducing your draw of kilowatt hours. So, it's a wash.
Because right now I have an example of someone who has solar, and he's getting paid like $20 a month. So he's actually using electricity normally, but we can't say that what he's using is above or is below what he's using. That's
Well, if you get paid about $20 a month. What you're doing is burning the meter backwards.
yes.
So he gets kilowatt hour payback for each kilowatt hour that meter's run backwards.
And after this, we have one question from the webinar audience.
I have kind of a really stupid question, but I work for communications company, and they have channels. Like if you want to talk to your cell phone, you have to get a channel. But if you want to make something more reliable, you usually double it up. And I see all your capital costs is in putting these big towers up and running these lines together, and then you put all your eggs in one basket by putting it all on the same channel. So has anybody ever considered the possibility of parallelizing some of this stuff? So you sign up for a different channel. If you want to get power, you've got to find an open channel where you can get some power on. Handle it more like a communication system. Just because it's power doesn't mean it's that different.
Well,
I don't hear it ever talked about. Maybe it's impossible.
It's cost. And since most of these are weather related, the other channels also overhead lines, and the weather, doesn't distinguish.
I think if you look at the capital cost, I think if they did it in the first place, when we put up the tower and put up more than one.
They have redundant lines.
Yeah. That additional cost is not so
Well, they do
great.
have redundant lines.
So you could provide, like we were talking about in India, you could provide a reliability channel where everybody would have like consistent levels of electricity. Now, there are different kind of events, different kind of problems with the faults and other things. Those things like that. That model wouldn't make much of a difference. But I don't see any thinking going along these lines.
And it really, economics is a huge driver. And the thing in India where they're doing, part of it's leapfrogging some legacy that they don't have to contend with. But it's a very good suggestion. If you give like 110 watts of power, which can do 3 or 4 essential items, nowadays.
Maybe you can multiplex frequencies on the lines you already have. I don't think anybody ever looked at that, where somebody could draw it 50, somebody could draw it 60, somebody could draw it 70, if you keep them all separate.
We'll do
Go ahead.
our last question from the webinar audience, and this is from Toyo Ateri. And he asks,
Other than preventing physical and cyber attacks on the grid, has there been a lot of focus on improving outage notification times to increase the overall reliability of the grid? This is specifically for cases like down power lines during a storm, which is more likely than, say, a physical or cyber attack. And yes, good job on your presentation.
Thank you, Tulio. So one of the things that is done in this area is providing the grid with the PMUs. So be able to see the grid in real time, basically. So that would help see the actual state of the grid at any time, which can prevent what the downwire. You can know it, so you have the notification that you can do something about it if you have the image of the grid.
Was that question directed to the small area stuff, right? Or was it to a big? It doesn't say.
He did not specify.
Okay, just for example, the local company here, PPL, has a system in place that if you're out of power, you can sign up and get a text message for the next of the power back on. It's obviously easy when it's one little local thing. When it's a big storm, though, they're also looking into that. They just started last fall. We had a presentation on the new smart metering systems are rolling out. We'll have a mesh network. They'll have a very much enhanced provide exactly that, because we've already got an automated dispatching system where each outage restoration effort is transmitted to a truck directly and managed by priority order by number of customers for how long. So, and customers who sign up for that notification can get an ongoing estimate and updates of power back on 2 or 3 days.
Thank you. Let's give it a round of applause. Connie, thank you. Hang on a second.
From one ESCI student to another. Just want to thank you for speaking today.
Thank you so much. Well done. Thank you so much.
You can see that we're gathering a web audience, and now it's kind of slowly picking up. And so next week seminar will be a webinar. This person will be remote. And students, by the way, are expected to be here, otherwise you won't get credit. Others could kind of tune in anywhere. I mean, you could have tuned in to this anywhere too. But student